Some problems are just, they feel impossible, right? But what if the answer isn't just throwing more power at it, but actually thinking about it in a smarter way? That's what we're doing today. We're going to crack open the programmer's toolkit and look at how we can solve these really, really tough problems.
Okay, so let's get the obvious one out of the way. Why can't we just, brute force it? Just throw a ton of computing power at a problem until it gives up. I mean, it sounds simple enough, doesn't it? But here's the thing. As problems get bigger, the time you need, well, it just explodes. We're not talking hours or days, we're talking years, centuries even. So yeah, we've got to work smarter, not just harder.
And that's a perfect lead-in to our first smart strategy, which is called dynamic programming. The easiest way to think about it? It's like giving our algorithm a memory, a way for it to stop solving the same puzzle again and again.
So you can see this fundamental trade-off right here. On one hand, you've got simple recursion. And yeah, it's elegant, I'll give it that. But man, is it wasteful. Like, if you're calculating a Fibonacci number, it just solves the same subproblems over and over and over again. Dynamic programming, though, takes a totally different approach. It basically says, whoa, hang on, I've seen this before. Let me just go look up the answer I already found. And this whole technique of remembering has a name. It's called memoization. Now, if you've ever dealt with databases, this is going to sound super familiar. It's just like caching query results, right? Instead of running a big, expensive query again, you just store the result and grab it from the cache. The idea is so simple, but it's incredibly powerful. You're just trading a little bit of memory to save a ton of time.
Okay, let's put this into practice with a classic puzzle, the knapsack problem. Picture this. You've got a bag, it's got a weight limit, and you have a whole pile of items, each with its own weight and value. The question is, how do you pack the bag to get the absolute most value? Well, dynamic programming just breaks this whole thing down. It figures out the best value for every possible weight using every possible combination of items, and it stores every single result. So here's the magic trick. When the algorithm finally gets to calculating the solution for your full knapsack, it's not starting from scratch. Nope. It's just looking up and piecing together the best answers it already found for all those smaller versions of the problem.
All right, so we've seen how being super methodical and organized can work. But what if? What if the best approach isn't methodical at all? What if we just introduce a little bit of controlled chaos into the mix? Well, welcome to the world of randomized algorithms. And this brings up a really, really practical question. Do you always need the absolute 100% perfect optimal solution? Or could a good enough answer, when you can find in a tiny fraction of the time, actually be more useful in the real world? And you know what? A lot of the time, the answer is a big yes. It's pretty amazing, actually. Just by injecting a little bit of randomness, say choosing a random place to start or taking a random path, you get these huge benefits. All of a sudden, the logic for your algorithm gets way simpler. It chews up way fewer resources. It's even fantastic for distributed systems where you can't possibly coordinate every little thing. It's kind of like you're engineering your own luck. So this whole idea leads to two main flavors of algorithms, and they're named perfectly: Las Vegas and Monte Carlo, because it really all comes down to a gamble. A Las Vegas algorithm? That's your safe bet. It will always give you the right answer. You just have no idea how long it's going to take. Then you have a Monte Carlo algorithm. That's the riskier bet. It'll finish in a predictable amount of time, guaranteed, but there's a small chance the answer might be wrong. So the choice is yours, really. Do you need to be sure about the answer or sure about the finish time? Now, this whole idea of finding good enough solutions becomes absolutely critical when you're up against the really, really big monsters. We're talking about problems with so many possible solutions that checking them all isn't just slow, it is literally impossible. And that's where something called local search comes into play.
These are a class of problems known as NP-hard. You've probably heard of the classic example, the traveling salesman problem. With these things, when you add just one more city to the trip, the time it takes to solve it doesn't just go up a little bit, it explodes exponentially. This is like a computational brick wall where brute force and even a lot of clever algorithms just throw their hands up and give up.
Okay, so the most intuitive way to tackle this is a technique called hill climbing. Imagine you're a hiker. You're on a mountain, it's super foggy, and your goal is to get to the highest peak. But you can only see what's right in front of you. What do? Well, you'd probably just take a step in whatever direction goes up the most, right? And you just keep doing that, always picking the steepest path up until you can't go any higher. But there's a catch. And it is a big one. What if you're not on the main mountain at all? What if you just climbed a little foothill? From where you're standing, it feels like you're at the top because every direction from there is down. You've hit what's called a local maximum, but the real highest peak, the global maximum, is way over on another mountain, and simple hill climbing gets completely stuck right there.
So, how do we get our poor hiker off that tiny foothill? Well, there's this brilliant technique called simulated annealing, and it's actually inspired by the process of forging metal. Think about it. When metal is red hot, its atoms are just bouncing around freely. But as it cools, they settle down into a really strong, stable structure. This algorithm does the exact same thing. It starts with a high temperature, which lets it make random, sometimes even bad moves, like, say, taking a step downhill to get off that foothill. Then, as the temperature cools down, it gets pickier and becomes less likely to take a step backwards. Eventually, it settles into what we hope is the true global best solution.
Okay, for our final technique, we're going to switch gears completely. We're moving away from exploring these big, foggy landscapes and into a world of optimizing within a really strict set of rules. This is for all those real-world problems where you're dealing with things like limited resources, tight budgets, or not enough time. Let's talk about linear programming.
Linear programming is just this incredibly powerful way to find the absolute best outcome when you're working within limits. So think about trying to maximize your profit, but you only have a fixed budget to work with. The key here, and it's a big one, is that both your goal and all your limits can be written down as simple linear relationships.
And the process for this is super structured, almost like a recipe. First, you define your goal. We call this the objective function. What is it you're trying to maximize or minimize? Then you list out all of your limitations, your constraints. You take all that, translate it into a neat mathematical model, and then you just let a solving algorithm go to work and find that perfect sweet spot, the exact mix of inputs that follows all your rules while giving you the absolute best result. And I want to be clear, this is not just some abstract theoretical thing. Linear programming is the engine running behind the scenes on a ton of real-world stuff. We're talking about how shipping companies figure out the most efficient routes, how marketing departments allocate their budgets for the biggest bang for their buck. It even helps build optimal investment portfolios. It is genuinely one of the most widely used algorithmic techniques in the world. So let's recap. We've talked about remembering past solutions, embracing a bit of randomness, searching cleverly for good enough answers, and optimizing within a strict set of rules. Wow, we've covered a lot of ground. And it all leads me to one last question for you. What's that big, messy, what feels like an impossible problem in your world that's just waiting for one of these smarter approaches? Definitely something to think about. Hey, if this explainer got you thinking about tough problems a little differently, do us a favor and hit that like button and subscribe so you don't miss what's coming next. And of course, feel free to share this with anyone you know who just loves a good, hard puzzle. Thanks for watching.